Hello guys, good morning. Good morning to all of you. Can you hear me properly? Can you hear me properly? So today in this session, we'll be discussing the first part of hydrogen atom. And this is one of the most important topics from quantum mechanics. Many times questions came from this particular topic. And this is easy. Look, as I told you in the beginning of our course, this quantum mechanical course, that if you can understand the mathematical aspects, mathematical tools of quantum mechanics and the postulates of quantum mechanics, then the remaining things will appear to be super easy if you can genuinely understand those things. And I hope you have understood it very well, and that is why the upcoming topics will appear to be very easy for you. Good morning, Karthik, Murli, Harry. Audio all clear? Okay. So let us start with this hydrogen atom. Whenever we talk about hydrogen atom, hydrogen has three isotopes: protium, deuterium, tritium. So whenever we are talking about hydrogen atom, means we are mainly referring to protium. Okay, 1H1. This is actually a hydrogen. So it has, you can see, one proton and one electron. There is no neutron. So if you visualize, let's say, the nucleus, so it is like this. So we have a proton at the center and the electron is revolving around it. Like this. Let's say we are also showing the electron. So here we have the electron in of charge -e, and here we have a proton of charge +e. This is the proton we have, and this is the electron we have. Now between proton and electron, what kind of force will be acting? Obviously it will be electrostatic attraction in nature. So the potential of a hydrogen atom system is, the Coulomb potential. We have to put it into Schrodinger equation, and in Schrodinger equation, what do you require? You require V of R. So here we need V of R. So this is, what is the potential energy between these two, proton and electron? 1/4πε0 Q1 Q2 by R. So Q1 Q2 is +e minus E square divided by 4πε0 into 1/R. So this is the potential. Now we have to plug in this potential into the Schrodinger equation. So the Schrodinger equation for electron in 3D. So you see, we used to write d square psi by dx square. Okay, d square psi by dx square, but I am writing in 3 dimensions, so it becomes del square psi by del x square plus del square psi by del y square plus del square psi by del z square. Okay, because we are dealing with 3-dimensional case, plus twice m by h cut square E minus V of R, let's say V of psi is equals to 0. Can I write it? So this is in Cartesian coordinate, right? This is the equation Schrodinger equation in 3 dimension in Cartesian coordinate. Sorry. The same Schrodinger equation we can express in spherical polar coordinate. And what will be the form in spherical polar coordinate? Spherical polar coordinate. The Schrodinger equation takes the form. So it is actually Laplacian of psi, right? And Laplacian in spherical polar coordinates, you know how to write. 1 by r square del r, r square del psi by del r, plus 1 upon r square sin theta del theta sin theta del psi by del theta, plus 1 upon r square sin square theta times del square psi by del phi square, and plus this thing does not change, twice m by h cut square e minus v psi is equals to 0. Okay. Now we are doing a little bit of calculation. So we are multiplying r square sin square theta on both sides of this equation. So r square sin square theta, if you multiply, then this will become sin square theta del r, r square del psi by del r, plus r square sin square theta. So one sin theta will survive here, sin theta del theta sin theta del psi by del theta, and 1 by r square sin square theta. So r square sin square theta is cancelled, so you are only left with del square psi by del phi square, plus twice m, we have multiplied r square sin square theta, and this h cut square is remaining. Now you see it is E minus V. So E minus V, V is equals to minus E square by 4 pi epsilon naught R, so minus minus plus, so E square by 4 pi epsilon naught R times psi is equals to 0. So you can see this is a second order differential equation. Now the solution of this, what kind of form it will take? The solution, so you see, one can solve. What technique we are going to use to solve this? We can use the separation of variable technique. R, theta, phi, these are the variables, they can be separated. So one can solve the above equation by the separation of variable technique, separation of variables technique. So you see, obviously the solution will be psi, right? Now psi is a function of r, theta and phi. Okay. Psi is a function of r, theta and phi. This is the solution of this equation. Now we are using separation of variables. So some function of r, some function of theta and some function of phi. So we are separating in this way, we are writing it as some function of r, capital R of r, and this is capital theta. Okay? This is written in this way, which is a function of small theta, and capital phi, a function of small phi. And so we can just write let psi of r theta phi equals to this. Now if you plug in this into this equation and do some calculation, you will get three equations, each for theta, r and phi. After plugging this into the differential equation, above differential equation, we get the following equation. Okay, so we will get three equations, one for r, another for theta, another for phi. So let us first write the equation for phi. What will be the equation for phi? So equation for phi will somewhat look like this. D square phi by d phi square plus ml square phi, this is equals to 0. Next, equation for theta. Sorry. 1 upon sin theta del theta sin theta d theta by d theta. Look, now theta, capital theta is only function of theta. That is why you can write d capital theta by d theta plus L into L plus 1 minus ml square sin theta. We have like jumped a long calculation. No, that is not necessary for you guys. If you are interested, you can check any standard textbook, or you can also let me know. I will provide you if you are interested. Otherwise, there is no requirement. We just need to interpret the final results. What remains? Equation for r. It is 1 by r square d r square dr by dr plus twice m by h cut square e square by 4 pi epsilon naught r plus e minus L into L plus 1 divided by r square times r equals to 0. Okay, here also instead of writing del theta, you can write d theta, because it is only involving theta part. Now these three parts will have three different solutions. Firstly, the solution for phi part. The solution for phi part. Look, what is our job? Our job is to find out the solution for all these three variables. We have to find out phi, we have to find out for theta, we have to find out the solution for r. then we can put it back into this equation to get the complete solution psi of r theta phi. So you understood the scheme? This is the scheme we are looking for. So it is capital phi, which is a function of small phi. The value will be 1 upon root 2 pi e to the power I ml phi. So the exponential part you see in the hydrogen atom solution is coming from this phi part, where this ml can take the value 0, plus minus 1, plus minus 2, plus minus 3. So it will depend upon the value of L. Okay, it will vary from minus L to plus L. So this is the solution for phi part. What about the solution for theta part? Look, there are long thing into the detailed solution of this, but we are avoiding, otherwise it will take many hours, and that is not so much useful also. That is why we are not doing the solution for theta part. What will be the solution for theta part? Capital theta, a function of small theta, this is equals to a times PLM cos theta. What is this PLM cos theta? PLM is the associated Legendre function. Associated Legendre function. Now PLM of cos theta, it is not like it is multiplied as a cos theta, it is a function of cos theta. So the original thing PLM of x, the original thing is written as PLM of x. So x is a variable, here the cos theta will be variable, it will be 1 minus x square to the power modulus of m by 2 d dx to the power modulus of m PL of x. What is this PL of x now? PL of x is the Lth Legendre polynomial. Lth Legendre polynomial. Try to understand the difference. Defined as PLM is the associated Legendre polynomial, a function. PLX is the Legendre polynomial of order, let's say L. Now it is given by Rodrigues formula. We have done it in mathematical physics class. PL of x. We have done it with Pn of x. Now, so here n is replaced by L. So 1 by 2 to the power L to L factorial d dx of L x square minus 1 to the power L. Okay. So the first few values you already know, like P0 of x is equals to 1, P1 of x is equals to x, P2 of x is equals to half time 3x square minus 1, and so on. So you see, this r and theta and phi, r is called the radial part of the solution, r for radial. This theta and phi, these two are combiningly known as the angular part. This is radial part, this is angular part. Theta and phi is the angular part. So we can now classify it into two categories. One is the radial part of the solution and angular part of the solution. So we get, we have written the solution for phi part and theta part. So if you multiply, we will get the angular part of the solution. Combined angular part of the solution combined angular part of the solution, let's say solution means the wave function, right? Combined angular part of the wave function is given by, it is expressed by spherical harmonics. We have already introduced spherical harmonics before also. Spherical harmonics, which is given by YLM theta phi. I told you that we will discuss this later also. So this spherical harmonics is given by YLM theta phi. You can see it is having theta and phi both variables. So this is the angular part. Acha, one thing needless to say, but let me say it here. The actual thing is appearing PLM of cos theta. So PLM of cos theta, this value you can write it in this way, that this is minus 1 to the power m sin theta to the power m d cos theta to the power m PL of cos theta. Okay. Look, 1 minus x square, 1 minus cos square theta. So that is I sin square theta, and this 2 is taken care of. So YLM of theta phi, this is the angular part of the solution. Now we need to know about this YLM of theta phi. Many questions come from this. First thing first, YL, if you write minus m, what is the relation between YL of minus m and YLM? This is minus 1 to the power m y LM. Now while we write the complete solution, we will require this spherical harmonics. Okay. Now orthonormality relation for this spherical harmonics. Look, orthonormality relation for spherical harmonics is given by, say YLM, it is a function of theta and phi. What is the limit for theta? It is 0 to pi. What is the limit for phi? It is 0 to 2 pi. So this is the limit for theta, 0 to 2 pi. This is the limit for phi. So this is YLM of theta phi multiplied by YL prime m prime of theta phi, then sin theta d theta d phi. This is equals to delta LL prime delta MM prime. This is the orthonormality relation for spherical harmonics. L is the azimuthal quantum number, M is the magnetic quantum number. You already know it. So this actual value of YLM of theta phi, how it is given? Now if you are getting confused, what is YLM of theta phi? You see, it is R of R into YLM of theta phi. This YLM of theta phi contains both theta and phi, right? Okay, is there any question till now? This topic is little bit odd, but the question which we will be doing will be very easy. Karthik, Murli, Hari, is there any question till now? Is there any difficulty in understanding till now? Tell me. These derivations, do you require for solution? We are not doing the derivations. I am just giving you those information which are necessary to solve CSR problems. Okay, not less, not much. Whatever you require, that is I am trying to give you in a very simplified way. Otherwise, if you start going to read everything, you may find it difficult. Okay, I am trying to make it as simple as possible for you in an organized way. Detailed solution you can look for in Griffith's book. In Griffith's book it is given. Okay. Now you see, what did I tell you? How did I tell you that y lm of theta phi is the angular part of the solution? Means you can imagine it in this way, that y lm of theta phi, it is the product of theta and phi of phi. So you see, in the theta part we have a times PLM of cos theta. It is some big constant. It has some expression. So क्या सर्दी हो जाता है. And this 1 by root 2 pi e to the power I ml phi for the phi part. So this spherical harmonics, it can be written. If you want, you can remember. Otherwise, if you don't remember, that is not necessary. Okay? For the sake of completeness, I am just providing you the expression of y lm theta phi. But we do not actually need to remember this. Epsilon square root of 12 plus 1 divided by 4 pi L minus modulus of m factorial divided by, I think we have provided this formula before also, e to the power I m phi. So this is coming from the phi part, and P L m of cos theta, where this epsilon has the value minus 1 to the power m for m greater than 0, and this is equals to plus 1 for m less equals to 0. Now we need to remember the first few spherical harmonics. First few spherical harmonics. Why it is important? You see, what kind of question you are given. The spherical harmonics has the dependency of I only via this exponential of I m phi, right? So if you get to know this term, you can easily tell what is the value of phi. Okay, and from others you can predict the value of L, and if you know the orbital angular quantum number, then you can easily get the angular momentum. So the first thing first, y0 0, y0 0, what does it mean? L is equals to 0, m is equals to 0. So it has a value of 1 by square root of 4 pi. It's a very standard result. If you put L is equals to 1, m is equals to 0, this gives you square root of 3 upon 4 pi cos theta. As you can see, we have put, as long as you put m is equals to 0, e to the power I m phi will be 1. So that is why this exponential factor will not come. As you make it L is equals to 1, m is equals to, let's say, plus minus 1, plus 1 or minus 1. This will give you, if you choose plus, it will become minus. If you choose minus, it will become plus. So minus plus square root of 3 by 8 pi, theta dependent sin theta, and obviously exponential. You see, m is equals to plus minus 1, so plus minus I phi will come. Next, if you take y2 0, m is equals to 0 again, so obviously exponential dependency will not be there. So this is square root of 5 by 16 pi 3 cos square theta minus 1. Okay. To get more insight, we can take another example. Y, let's say 2 plus minus 1. So m is not equals to 0 here. So obviously plus minus, so minus plus, then some constant square root of 15 by 8 pi. Okay, sin theta cos theta e to the power plus minus I phi. Okay. So let me, along with this, let me also provide you the value of associated legendary polynomial. Although that is not necessary, you can just remember this. But to understand how these terms are coming, associated legendary polynomials. You see, P00 of cos theta, P00 of cos theta, this is equals to 1. P10 of cos theta, because you see this thing has been calculated by taking into account this. So you should know little bit about it. P11 of cos theta is equals to minus sin theta. Okay. P20 of cos theta is equals to half into 3 cos square theta minus 1. P21 of cos theta, this is just for your information, don't take too much stress about it. 3 cos theta sin theta. No need to remember, just for the sake of completeness, you just note it down. In future may be useful, but even if you don't remember, that will not affect you in any way. 3 sin square theta. One last, where do I write? Here I am writing P3 0 cos theta half 5 cos cube theta minus 3 cos theta. This yellow thing, I think you are not able to understand. P3 power 0. No. It is PLM, right? PLM. L value is 3, M value is 0. It is not power. Those are the value of L and M, na? Associated Legendre polynomials P, L, M of cos theta. It is not power. Just a representation. Any more question, guys? You can ask me any absurd question you are getting, you can ask. It may appear to be absurd, but it may be useful. Okay, don't keep any doubt with you. So try to look at these values very carefully. If it is only 1 by root 4 pi means y L value is 0, M value is 0. If you see somehow that only cos theta is there, what does it mean? Obviously it is referring to y10, means L value is 1, M value is 0. If you see something, look, this scaling factor is very difficult to remember. What is the value of root 3 by 8 pi? It is difficult to remember, but you can remember that if you see sin theta exponential of something, you can easily say it is referring to y1. Maybe if you have plus here, it is y11. If it is minus here, then you can say it is y1 minus 1. So from this we can predict the value of L and M. And that is what you need. I am giving you one problem, then you will understand it very clearly. A particle moving in a central potential is described by psi of r is equals to z times f of r, where r is the Poisson vector of the particle, f of r is a function of r, L is the total angular momentum of the particle, the value of L square must be. So L square means what you have to find, L into L plus 1 h cut square you need to find. Okay, so you need to find first L. L how will you get? From this expression of psi. Look, we have done for the angular part. Angular part is y Lm of theta phi. What remains? The radial part. Okay, radial part will see that it is a function of RNL. You will get to see later on. Okay, so for the timing I am just writing it's a radial function r of r. So psi of r is equals to z times f of r. F of r is the radial part. So the angular part is coming through z. So represent z with in spherical polar coordinate, then you will get to know the value of L by comparing with the spherical harmonics. Do it, give it a try. Could you do this? Tell me the answer. Look, I think you can easily do it. Very simple problem. Given wave function psi is equals to z times f of r. So we have nothing to do with f of r, that is radial part. Let's keep it separate. So this is f of r, z is what? If you express it in spherical polar coordinate, z is equals to r cos theta, right? So r into f of r, this will come under the radial part, only angular part is cos theta. So where do you see cos theta? We see it at one place, this y10 equals to square root of 3 by 4 pi cos theta. Okay na? So we can say here the angular part of the wave function, what will be the answer? I think you should have done it by now. Phi of theta phi, this is equals to cos theta, and you know this is proportional to y10, as you have seen here, y10. So if y10 it is proportional to y10, so we can say that L value is obviously 1, M value is obviously 0. So if you know L value, so we can easily calculate L square, L into L plus 1 h cut square, 1 into 1 plus 1 h cut square, so 2 h cut square. So if you see, if you know that knowledge, if you have the desired knowledge, you can solve it maybe in less than 30 seconds. Got it? So that is why I am telling you to remember the first few spherical harmonics. This much will be sufficient. Rather than remembering things, you need to remember the pattern. Like if you don't fully remember square root of 3 by 4, if you remember that cos theta means y10, sin theta to the power I phi means it is talking about y11, sin theta to the power minus I phi means it is talking about y1 minus 1. Okay, if you see 3 cos square theta minus 1, no exponential dependence. If you don't see an exponential term, you will think that m must be 0. You see, no exponential part means m equals to 0. Here the m part is non-zero, means exponential part will be there. So you need to have that observation skill. So till now we have focused on the angular part. Let us now focus on the radial part. The radial equation. Look, if you have a spherically symmetric potential, then the theta and phi solution will be same. The actual factor which will actually define the potential is coming from the radial part. What I want to mean, let us just write, so for your future reference, that the angular part of the wave function, we are doing this topic from Griffith's book. Okay, notice that the angular part of the wave function y lm of theta phi is the same for all spherically symmetric potential. It is not just true for hydrogen atom problem, but it is true for all spherically symmetric potentials. So if it is so, the actual shape of potential V of R affects only the radial part of the solution, only the radial part of the solution, means the wave function given by R of R, which is determined by let us write the radial equation we have already written, ddr of r square d capital R by dr minus twice m r square by h cut square. We had V of r minus E times capital R is equals to L into L plus 1 of capital R. Okay. So this minus sign is coming because we have written V first. Now to solve this equation, we need to change the variable. How to change the variable? So we can let's say from R we want to go to U. U is defined as R times capital R or small r. So capital R of R is nothing but U by small r. So you require dr by dr. So let's write dr by dr. Derivative with respect to r. So r square will come here. Then what you have, r into du by dr minus u into dr by dr. That is r square times d capital R by small r is equals to r times du by dr minus u. So this part we have calculated. Now we have to take derivative with respect to r of this whole thing, ddr of r square dr by dr. I am doing it in a very simplified step so that you can understand. Derivative with respect to r. So you see r times d square u by dr square plus, if you keep du by dr, so du by dr by dr is 1 minus this u du by dr. So you can see this is cancelling. So you are left with r times d square u by dr square. So if you plug in this value into this equation, what you gonna get? Therefore, okay, so putting these values, into the radial equation, we get, what will you get? You see this minus h cut square by 2m, we are taking it here. So minus h cut square by 2m, and this whole thing is nothing but this r times d square u by dr square, isn't it? So that r is somehow divided and absorbed in other parts, plus v plus h cut square by 2m L into L plus 1 by r square times u is equals to E times u. So you will be getting this kind of expression. If you put this value d dr of r square dr r into d square of u by dr square, if you make it free of r and adjust the calculation, you will get it. This is actually called the radial equation. Now this equation is particularly very important. This is known as radial equation. Now why did we require to represent it in this form? Because previously we had this form that was not so familiar to us, but after making these changes of variable, we have turned it into a very familiar form. So it is identical with the form of the 1D Schrodinger equation, right? It is identical in the form to the one-dimensional Schrodinger equation, except what is the difference? You see, it so in Schrodinger equation it had v of psi, right? V of u. This extra h cut square by 2m L into L plus 1 r square, this is an additive term. So we can say that we can express it like effective potential to make it exactly identical with the form of 1D Schrodinger equation. So except the effective potential. So this term in whole v plus h cut square by 2m L into L plus 1 r square, it is called the effective potential. Effective potential, how do you define? V effective is v of r plus h cut square by 2m L into L plus 1 by r square. So it is identical in the form to the Schrodinger, only Schrodinger equation, except the effective potential. This, it contains an extra piece. What is that extra piece? H cut square by 2m L into L plus 1 by r square. This is known as the centrifugal term. Centrifugal term. H cut square by 2m L into L plus 1 by r square. So what is the purpose of this centrifugal term? You know, what does the centrifugal term do? It pushes the particle away from its center. Okay, now electron is revolving around the nucleus, means proton. So obviously we should get some centrifugal part. So it tends to throw the particle outward, that is away from the origin, just like the centrifugal, which is a pseudo force in classical mechanics. Okay. So if you plot it in a diagram, the effective potential, if you plot, so what kind of shape you will get? If you plot, let's say V effective here, V effective versus R. So this will look like this. We have done it in classical mechanics, right? Something like this. Sometimes we need to know about the energy level of hydrogen atom. You already know, in atomic physics we have done it. What is the expression for the hydrogen atom energy? Sometimes it may be useful. So let's just write the formula. Okay. Energy of hydrogen atom. It is given simply by this formula. Let's say En equals to minus 13.6 by n square electron volt. So ground state is minus 13.6 electron volt. Any question, guys? Let's solve some problem. This came in June 2011. The energy levels of the non-relativistic electron in a hydrogen atom, that is in a Coulomb potential, are given by E ln m minus 1 by n square. You can see the energy level is minus 13.6 by n square. So that is proportional to minus 1 by n square. Okay. Coulomb potential minus 1 by r minus E square by 4 pi epsilon naught r, you have seen. N is the principal quantum number and the corresponding wave function is given by psi n l m, where L is the orbital angular momentum quantum number, m is the magnetic quantum number. The spin of the electron is not considered. Which of the following is a correct statement? Can you do this? What do you think? What should be the answer? Just think a little bit. Based on the theory I gave you, I think you should be able to solve this problem. There is a unique wave function for psi NLM for each E NLM, is it? The hydrogen atom has degeneracy of n square, right? Look, here the question is little bit critical. You need to have deep understanding. One thing I wrote, okay, where is that? Yeah. Angular part of the wave function is the same for all spherically symmetric potential. Actual shape of the potential affects only the radial part. Okay. Radial part depends what radial parts decide. Radial part is responsible for n. Okay, theta phi dependency gives rise to what? L and m. But the radial part is responsible for the principal quantum number n. And the energy, as you can see, energy is depending only on n. So obviously L and m will not decide. So ENLM does not depend on L and M for the Coulomb potential, because you can see it is proportional to 1 by r n square only. So option C will be the correct option. So write the explanation. The explanation is quite interesting. We know En is equals to minus 13.6 by n square electron volt. Now why it has n degeneracy? Why it has degeneracy of n square? It is not unique, right? Psi NLM for each NLM, it is how it is unique. So for principal quantum number n, the L value can be 0 to n minus 1, right? And for each L value, ML can run from minus L to plus L. So this, if you calculate, it will give you n square. So it is the degeneracy of hydrogen atom. So this is not unique. If you include the spin, it has two possibilities. So then becomes 2n square including spin. So obviously this option D is not the correct option. And this is also not correct. L into L plus 1 different wave function, that is also not correct. Let us write few more lines to make it more descriptive. The energy En depends only on n, not on L and M. This is due to the degeneracy n square, neglecting spin, that arises due to the spherical symmetry of the Coulomb potential. Spherical symmetry of the Coulomb potential, which depends only on radial distance r of the electron from the nucleus, which is considered to be the origin. There is no angular dependence Angular means of theta and phi in V of r. Okay. Why there are exactly this wave function for each element? Because this is not 12 plus 1. It is sum over 12 plus 1 that gives rise to n square. Okay. Because this is 1 for one L value. L value itself can run from 0 to n minus 1. So total wave function will be n square. If it had n square, then we can write. And this is just to just to distract you. L into L plus 1. The L square is equals to L into L plus 1 h square. So that from that they have picked up this. And this one 12 plus 1 they have taken from this. But actually the degeneracy concept is coming here. Now there is a slight modification to this problem. That came in June 2016. Same question. Suppose that the Coulomb potential of the hydrogen atom is changed by adding an inverse square term. So inverse square term has been added. So previously minus Jd square by r was there. Now this extra term has been added, G by r square. G is a constant. The energy eigenvalues in the modified potential will be. When this G by r square was not there, it was only depending on L. Now if G by r square is added, what kind of changes it will have? Actually this is perturbation question. Perturbation will be doing next. For the time being, just know this, the Hamiltonian of the hydrogen atom, potential energy is minus Jd square by r, but the kinetic energy is p square by 2m, minus Jd square by r. So this was the Hamiltonian for hydrogen atom, but here you see G by r square has been added. So plus G by r square. So this is the potential part, this is the kinetic energy part. So you can write it as H0 unpart of Hamiltonian plus this G by r square is serving as a perturbation. Perturbation we will talk about. Okay, for the time being you know this. There is something called unperturbed Hamiltonian and then perturbation. Just give me a moment, getting a call. Hello. Yes. Good morning. Sumit. हाँ बोलो सुमित. हाँ 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 वो पहले वाला मार्क्स जो आपका था उसी को रखा गया है ना, 22 या समथिंग मिला था ना आपको. हाँ हाँ वो मैं करा दिया हूँ, है ना. हाँ 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 सेम ऑन वाले में. नहीं नहीं सेम 2 वाले में होगा ना आपका. आपका जो सेम 2 वाला मार्क्स था ना उसको दे दिए हैं, जो अभी सेम 2 का जो मार्क्स था वो दे दिए हैं. अच्छा आज वाला आपका मार्कशीट में आया है मार्क्स, मतलब इंटरनल सेम 1 का इंटरनल का मार्क्स आया है. तो आया है तो आ जाएगा, और अगर आपको एग्ज़ाम देना है तो दे सकते हैं. बट वो पुराना वाला मार्क्स मतलब वो जो है ना कॉपी, वहाँ पे एक बार चेक कर लीजिएगा कि है या नहीं. तो अभी आप अभी क्यों पता कर रहे हो, पहले पता करने को बोला था ना. अच्छा पुराने जो आपका मार्कशीट है वहाँ पे अगर आपका मार्क्स मेंशन है इंटरनल का तो वो रिपीट हो जाएगा, वो आ जाएगा. हाँ वो आ जाएगा, रिकॉर्ड में रहता है। हाँ, एक बार आके विवेक सर से मिल लो, ठीक है। Sorry guys. This is equals to minus 13.6 by n square electron volt. Now this En of 0, this is coming from this unperturbed Hamiltonian. From the perturbed Hamiltonian you will get the correction. The correction is given by En of 1. This is a first order correction. We will talk about it in perturbation chapter very well. G into 1 by r square. This is equals to G times 2 by n cube 12 plus 1 a naught square. You just see the dependency of n and l. You don't need to remember this. So this type of problem is a little bit you can say informative. You see, previously we had no perturbation, only this unperturbed Hamiltonian was there. We are getting only n dependency, minus 13.6 by n square, n dependency we had. But now we have the perturbation, so obviously the energy expression will be changed. Along with this n dependency, we are also getting L dependency coming from the perturbed part. So we can say that En L M depends on n dependency, and you can see it has also dependency on L, but it doesn't have any dependency on M. So which option is it correct matching with? Depend on n and L but not on M. Option A. बताओ if it is understandable or not. Okay, let us now talk more about the radial wave function. We have talked about in detail about the angular part of the wave function. Let's now talk about the radial part of the wave function. Radial, or you can say also a spatial part. Question come from this. The spatial part of the wave function, spatial wave function for hydrogen are labeled by three quantum numbers n, l, m, principal, orbital and magnetic, labeled by three quantum numbers. What are those three quantum numbers? N, L and M. So the wave function for the hydrogen atom is written as psi n, L, M. The first number here will show the principal quantum number, L will show orbital angular momentum quantum number, M magnetic quantum number. It is a function of r, theta and phi. So it has the angular part and the radial part. Radial part is written as r n l, which is a function of r, and the angular part is given by the spherical harmonics y l m of theta phi. This is as simple as that. Okay. Harry, are you there? Where is Harry? Harry is not responding today. Now, you see, in this expression, if you choose, let's say, n is equals to 1, n is equals to 1, L is equals to 0, then what you will get? Psi n is equals to 1, L is equals to 0. If L is equals to 0, M will obviously be equals to 0. So psi 1 0 0, psi 1 0 0. So function of r theta phi, this is r, n is 1, L is 0, r1 0 of r, y L m, so y L is 0, m is 0 of theta phi. This is the ground state wave function. So y 0 0, you know the value, y 0 0, what is the value? 1 by square root of 4 pi, na? We have seen it, 1 by square root of 4 pi, remember that. So r 1 0 of r, this is the radial part of the function, it has also some functional value. So it has a value, let's say a prime by a naught e to the power minus r by a naught. Now this needs to be normalized. Normalizing it, so r can run from 0 to infinity, r 1 0 whole square r square dr. This is equals to mod a prime square by a naught square 0 to infinity e to the power minus 2r by a naught times r square dr. So if you calculate this thing, this will give you mod a prime square a naught divided by 4, and this is 1. So from this we can get the value, because it is normalization, so obviously the right hand side will be 1. So from this we can get the value of a prime to be square root of 4 by a naught. So 2 by square root of a naught. Now you see a prime we have got, a prime we have got, and y 0 0 is 1 upon 4 pi. Meanwhile y 0 0 1 upon square root of 4 pi. So what will be the value of psi 1 0 0, which is the product of r 1 0 and y 0 0. So r 1 0 is a prime by a 0, a prime you have got 2 by square root of a naught into 1 by a naught e to the power minus r by a naught, y 0 0 is 1 upon square root of 4 pi. And hence we get this value that the ground state of the hydrogen atom, you should remember this, okay, final form, what you will get, this is square root of 4, so 2 to get cancel, 1 upon this square root pi a naught square and a naught, so a naught cube e to the power minus r by a naught. So this is the ground state wave function of hydrogen atom. Ground state energy, you know, 13 minus 13.6 electron volt. Okay, so this you should remember, 1 by square root of pi a naught cube e to the power minus r by a naught. And if you only look for the radial part r10 of r, it is a prime by a naught, so it is 2 by a naught to the power 3 by 2 e to the power minus r by a naught. Okay, now you can see a prime you have put 2 by a naught, 1 plus half, so 3 by 2 e to the power minus r by a naught. So sometimes this may also be required, but I will recommend you to remember the this one. Okay, this is only the radial part. This is the combining angular part as well. Till now, is there any confusion, Murli, Karthik? This is just the ground state. We can write the most general expression for the wave function, but that is very critical. Too much to remember. Okay, the normalized hydrogen wave function is given by. So I am just giving this formula just for the sake of completeness, just for your information. You don't need to take stress about it, because the equation is very stressful. Psi NLM, this is equals to square root of 2 by n a naught cube n minus L minus 1. Why I am calling this equation stressful, you will understand it in a bit. 2n n plus 1 n plus L actually factorial cube e to the power minus r by n a naught 2r by n a naught to the power L, legendary function 2l plus 1 n minus L minus 1 2r by n a naught y lm theta phi. So there is no point in remembering this, so just keep a note. L 12 plus 1 n minus L minus 1. This is associated Laguerre polynomial. This is associated Laguerre polynomial. So if this is a wave function, what is the normalization condition for this wave function? The normalization condition is given by integration psi NLM star psi n prime L prime m prime r square sin theta, okay, r square dr sin theta d theta d phi. This is delta n prime delta ll prime delta mm prime, where n will run from, for hydrogen atom n starts from 1 2 3 and it will go up to infinity. L will run from 0 to n minus 1, 0 to n minus 1. M will run from minus L to L, so minus L minus L to L. Okay, so we'll be solving some problems, more problems, and some little bit of theory is also left in the. So we'll be doing that in the second part. For the time being, I am giving you a tabular set of tabulated values regarding this R radial part of the wave function. You see, we have shown you R10 because this is involved. This is involved in the ground state wave function of the hydrogen atom. So that is why it is especially important to remember 2 by a naught to the power 3 by 3 to the power minus r by a naught. So if you change the value of n and l, this r will be changed. So the first few radial wave function for the hydrogen atom is given by this table. The first few normalized radial wave function are NL of the hydrogen atom by choosing different values of n and l. If you choose n is equals to 1, L will be equals to L will be 0. So R10. N equals to 2, you take L will be 0, 1. Okay, for 0, this is the wave function. If you choose n equals to 2, you will get L is equals to 0 and 1. Okay, no? So actually it has shown for 0, then it has shown for 1. For 3, you will get 0, 1, 2. And you can see the form of this radial wave function. First one we have derived by doing the normalization and all. R20, if you want, you can remember. That will give you the idea of the first excited state. Okay. You just try to observe the dependency. Okay. Here you see minus r by a naught. Here you see minus r by 2 a naught. Minus r by 2 a naught. For n equals to 3, you see minus r by 3 a naught. So from this you can get little bit of idea about the value of n and l, right? When 1 a naught means n equals to 1. When 2 a naught, n is equals to 2. When 3 a naught, n is equals to 3. You can see here also 3 a naught, here also 3 a naught, and corresponding values are n is equals to 3. So in this way, for this kind of complicated expressions, you don't need to remember them exactly, but you need to observe the pattern so that you somehow get the value of n, l and n. Our main target is to get to know the value of n, l and m. That you can find out without remembering the whole expression. You just by looking at the pattern, we can get to know about the values of n, l and m. Okay. So this is all for this video, guys. I hope you find this session useful and you have understood everything. Thank you. Thank you very much. Have a great day. Bye bye. Take care.